Hi there, it's Miss Adams from Flamingo Math. Join me today in lesson 3-2. The first day, we're going to look at 6 examples all about sine, cosine, and tangent functions. Let's start with the verbal and visual vocabulary. A standard position is an angle whose vertex is at the origin of the coordinate system, and one of the rays is sitting on the positive x-axis. That's known as the initial side. That would be this side right here. The terminal side is the ray or the side of the angle that is not along the x-axis. That would be this ray right here. So we have the initial side and the terminal side. We're going to label that the terminal side. We usually use theta or alpha or beta. The Greek letters alpha, beta, and theta are usually used to label our angles. So this is an angle in standard position. And then the last bit of vocabulary, coterminal angles, that's when two angles in standard position have the same terminal side. And then a unit circle is a circle whose radius is 1 unit. Its center is at the origin of the coordinate plane, and points on the circle are related to periodic functions. In this example of a unit circle, 1, 0 would be on that graph, 0, 1 would be on the circle, -1, 0, and 0, -1. Let's talk about positive and negative angles. A positive or negative angle measurement tells the direction of rotation, and that's where the idea of coterminal angles could be. Positive angles are rotated in a counterclockwise direction. So if we start here with the initial side sitting on the x-axis, and our angle rotates around 5 pi over 4 or 1 1/4 pi. The terminal side is down here in quadrant 3. So the angle that goes from the positive angle, that negative rotation, in a clockwise manner, I could call that angle theta prime. It would rotate -3/4 pi. Those would be coterminal angles. Theta prime is called the coterminal angle, theta prime. Coterminal angle. So that's an example of our vocabulary word there. By picking a point xy on the terminal side of some angle theta in quadrant 1 in the xy coordinate system, if we draw a perpendicular from the point down to the horizontal axis, it forms a right triangle. So we've got the initial side on the x-axis, the terminal side is in quadrant 1, and you draw a perpendicular down to back to the x-axis. We can use the right triangle definition of the trig functions for acute angles. We're calling that theta. This is the distance from here to here. This distance is x. And from the x-axis up to the point, that distance is y. So the sine is going to be the length of the opposite side by definition. So the sine of angle theta is the length of the opposite side, which is the y, divided by the hypotenuse in this case, which is r. The cosine is the adjacent leg length divided by the hypotenuse length, and the tangent is the opposite leg length divided by the adjacent leg length. If we relate right triangles to the coordinate form, in our example here, we're letting x and y, the xy is the point r units from the origin on the terminal side of that rotating ray. So our angle starts on the x-axis, that's the initial side. It rotates around and stops at point P, and the xy coordinates has a length of r. If theta is the angle in standard position of the ray, then it follows that the sine is the y value divided by the length of the hypotenuse. And we just saw that in the previous example. Sine is the length of the opposite side divided by the length of the hypotenuse. And cosine is the length of the adjacent side divided by the length of the hypotenuse, while tangent is the slope, or if you want to think of it as a ratio, it's the sine divided by the cosine, or the y value divided by the x, the rate of change. Rise over run. For example 2, we have the figure shows a circle with radius r centered at the origin with an angle measurement theta that's in standard position. The points M, T, and H are the result of reflecting point A across the y-axis, across the origin, and then the x-axis respectively. If you think about labeling those, point M would be a negative x value and a positive y. Point T would have a negative x coordinate and a negative y coordinate, and point H would have a positive x coordinate and a negative y coordinate. So we can record that here in our notes. Point T is negative on x and y, and point H is negative only on the y. For example 3, if we use that image, we can find the following: the sine of the angle whose terminal ray intersects the circle at point H. If you draw yourself a little sketch down here, the terminal side at point H is down here in quadrant 4. This is my angle. I'm going to call that beta sub 1. We have an x value, we have a perpendicular, which is the y value, and we have the length of the hypotenuse, which is the r value. So the sine of the angle beta sub 1 would be negative on y divided by the length of the hypotenuse, because our y value is negative down here in quadrant 4. The cosine, if we called that cosine of, let's say, beta sub 2, for point M, we're up here, so beta sub 2 would be a sketch in quadrant 2. So the angle comes over here. We're stopped at point M. We're dropping the perpendicular back to the x-axis. So we have x going in a negative direction, y positive, and r. The cosine is this is my angle, beta sub 2. The cosine is the adjacent side divided by the length of the hypotenuse. And then finally, for tangent, the tangent of an angle that ends up at point T is going to be in quadrant 3. So making a sketch of that, we're down here in quadrant 3, dropping the perpendicular back to the x-axis. Our angle, we're going to call this one beta sub 3, and we're moving left on x and down on y, and the hypotenuse is r. So the tangent of angle beta sub 3 is negative y divided by negative x, or a positive over a positive in that case. Example 4, the figure at the right shows us a circle with radius of 5. Centered at the origin, and the angle of measure theta is in standard position. The terminal ray of the angle intersects the circle at point Q. We want to find the sine of theta. So sine, if this side is 5, hypotenuse is 5, hypotenuse is 5, this height is 3, this length is 4, but it's in the negative direction. So we went 4 left and 3 up. The sine would be the side opposite divided by the hypotenuse. The cosine would be the side adjacent divided by the hypotenuse. And tangent would be the side opposite divided by adjacent, so negative 3/4. Our point Q is located at negative 4, 3, just for the reference. For example 5, the figure shows a circle centered at the origin with an angle of measure beta in standard position. The terminal ray of the angle intersects the circle at point P. Which of the following is true about the sine of beta? So the terminal side, we come all the way around here. This is our angle beta. This is x. This is y in a negative direction. And the circle, what was it, is length 4, looking at the information down here. So what is true? Is the sine of beta x over 4? Well, the sine is the length opposite divided by the hypotenuse. You may know the mnemonic SOH-CAH-TOA, SOH-CAH-TOA, which gives us that easy way to remember opposite, hypotenuse, adjacent, hypotenuse, opposite, adjacent. So is the ratio, this one is false. The sine of beta is 4 divided by x. So hypotenuse divided by adjacent, that's false. The sine of beta is negative y divided by 4. So sine is opposite over hypotenuse. I believe this one is true. Let's see, so that is true. Whoop. That's not a good color. C is the true one, because the ratio of the vertical displacement of P from the x-axis to the distance between the origin and point P. That one is true. So the sine of beta is the length of y divided by the length of the radius. So part C was true. And example 6, I believe this is our last example. Let alpha be an angle in standard position whose terminal ray coincides with the line y equals negative 2x. In quadrant 2, we want to sketch that scenario. And looking at this image, we know that this angle is alpha, dropping the perpendicular back down to the x-axis. This height is y. We got that right triangle. This length is negative x. The line is y equals negative 2x. And we need to find a name for our r value. That should turn out to be r divided by the square root of 5. And here's how we can think about that. Since they gave us y is negative 2x, and we know the equation for a circle is x squared plus y squared is r squared. If you substitute negative 2x in for the y value, let's just replace this with negative 2x. So we got x squared plus 4x squared is r squared. We have 5x squared is r squared. If you divide both sides by 5, and then take the square root of the left and the square root of the right, x is going to be the square root of r squared is r divided by the square root of 5. Now think about that in quadrant 2. We know that x needs to be negative in quadrant 2. And then the value for sine is opposite over hypotenuse. So we've got to figure out the hypotenuse. We're calling that r. This is our hypotenuse. Sine is opposite the length of the opposite side, which is y in hypotenuse. So y over hypotenuse, but they told us y is negative 2x. And then what did we know about x? X is negative r over the square root of 5, and we're dividing by r. So the r's are going to cancel out, and 2 over the square root of 5 would be our value for the sine of the function. So 2 over radical 5. Cosine, let me erase some of this so we can have room to write. So cosine of alpha is adjacent over hypotenuse. Adjacent side is the x value, and we said x is negative r over the square root of 5. So adjacent over the hypotenuse, which is also r. So negative over r, that's going to be negative 1 divided by square root of 5 when we simplify this issue. Then tangent we said is the slope, and if slope is change in y over change in x, but we know y is negative 2x, then the slope is negative 2. So sine is 2 over radical 5, cosine is negative 1 over radical 5, and tangent is negative 2. And that completes day 1 for sine, cosine, and tangent.